So, Asim, is it visible? Okay, fine.
Yes, sir, it's okay now.
Okay. So, we were doing operators last time. We talked about the rotation operator, right? Let's uh, do an example today for the rotation operator. Right? We are going to do an example so that we understand what is the rotation operator. Write down R 5/2 into R in matrix form. We have to write this in matrix form, right? Okay, so we know that the matrix of a rotation operator, right? If we have 3 dimension in 3D, right? In 3 dimensions. So we will have something like this. Rotation operator 1 R 1, right? 1 R 2 1 R 3 and 2 R 1 2 R 2 and this 3 R 1 and 3 R 2. Right? That will be the operator for the 3-dimensional rotation operator, right? That will be the matrix form. Now we know that we have to find it for this thing, right? So we know R equal. This was equal to. We said if we take the frame around vector 1, around kit 1, or around I, we said, right? So if my thumb represents, we have done this, if this represents the kit 1 or the I vector, I direction, or in other words, X direction, then Y and Z are in the plane of the board. If we rotate it around I, then it does not change I, right? So R of 1 will be equal to 1, right? And we have done this. R of 2, if you remember, this was equal to 3, right? And R of 3, if you remember, it was equal to -2, right? Now we put these things here, right? So this will be equal to 1, and R of 1 is 1, and here 1, R of 2 is 3, and 1, R of 3 is -2. So I will write minus k, then 2, and R of 1 is 1, right? And 2, and R of 2 is 3, and then 2, and R of 3 is -2, right? See, R of 1 is 1, and 3, R of 2 is equal to 3, and here 3, and R of 3 is equal to -2, right? So we can write this. 1 with 1 will be equal to 1, right? Because they are normalized like this. I multiply by I dot I, that's the inner product or the scalar product, right? And 1 I dot j will be equal to, I dot k will be equal to 0. Similarly, I dot j will be equal to 0. This will be equal to 0. This will be equal to 0. That is equal to minus 1. That is 0. That is 1. And that is 0. So that is the matrix for the rotational operator, in which we rotate the matrix, we rotate the system, right, by pi by 2 around I-axis. So this operator represented in matrix form is this one. Okay, I am giving you homework, right? And that is you have to find the right homework exercise 1.6.1, right? Omega is equal to 0, 0, 1, 1, 0, 0, 0, 1, 0, right? What is the action of this operator? That is the exercise. Now, we want to write important operators in matrix form, right? Important operators in matrix form. Right? Okay. Number 1, the identity operator. Identity operator. Right? The matrix element of the identity operator, if we represent the matrix element of the identity operator by ij, the I column and j row, that will be equal to, you can obtain it by I, right, and to I and to j, right? R, we know what is the action of I on j? That is j. So it is I and j. So the ith, the element of the identity matrix, and which lies in column I and row j, that will be equal to this thing, R delta ij. So you get the element of the identity matrix by delta ij, right? And which means that if I is equal to j, it is equal to 1. If I is not equal to j, it is equal to 0. So identity matrix, each element, if it's a 3-dimensional, suppose it is a 3-dimensional matrix, identity operator, matrix form, right? So, like the first element will be equal to 1 because it will be delta 1, 1. The second element means, the first row and second column, that will be my second element. That will be equal to 0 because I will be equal to 1, j will be equal to 2. The third one will be I equal to 1, j is equal to 3. So again it will be equal to 0. Similarly, the first one of the second row will be I equal to 2, j equal to 1, will be equal to 0. Then the second row and second column, right? That element will be 2 and 2. So I2, 2, that will be equal to delta ij, and delta 2, 2, that will be equal to 1. Similarly, you will get the delta 3, 3 equal to 1. So the identity element is represented by, For example, if we have three-dimensional, right? So identity matrix will be like 1 0 0 0 1 0 0 0 1. That will be the sum of the identity matrix. Okay, now let us discuss another important operator, the projector operator. Let us revise the projection operator and do it a little bit in detail here. So we know that we have done any vector can be written in terms of its components, right? And we say that is equal to vi into I hit vector I. I starts from 1 goes to n, right? Okay. We can, this is just scalar quantity, we can write it here. I start from 1 goes to n, right? R, we know that Vi is the scalar product or the inner product of the ith dimension with the vector V. So we can write this like that. I is equal to 1 after n. So vector V is equal to, look at this, vector V is equal to something multiplied by the same vector. So we can say that something acting on the vector V is giving you the same thing. So here we get a very important result. We can say that this is like identity operator. Identity operator acting on a kit, giving you the same kit. So this is like an identity operator. So we can say that I and I start from 1 goes to n, and that is equal to I. Right? So it's like the identity operator acting on the kit and giving you the same kit, right? Or if we call it the projector operator PI, right? We have done this, now we are just repeating it. If I and I is equal to PI, the projector operator along the dimension I, right? Then this I here will be equal to, from here, I equal to 1 up to n, and then is pi. The summation of all the projections in a vector space is equal to the identity matrix or the identity operator. This is a very important result. We will use it a lot. A very important result, very useful result. Very useful result. We will use it. Right? So keep this in, connect this to your memory. Right? I will say PI, right? Is equal to this. And we call it the PI. The projector operator. So the sum of the projector operators, right, for all the dimensions is equal to identity operator, right? And this is called this equation or this equation. They are called the completeness relationship. The completeness relationship. This is they both are called the completeness relation. They are the same thing. We will use this a lot. You will see what does it mean when we go ahead. So we are discussing the projector operator. We will then find what is the matrix form of this. Right? So the action of the projector. What is the action of the projector? Right? Okay, we say PI acts on a kit wing. Right? It is like this. Projector operator is this thing. I and wing. Now we can look at this. What is this? This is the component of V along I. The component of V along I. And the component of V along I, we call it VR. Right? So, the projector operator, the action of the projector operator is it gives you the projection of that vector on the dimension of which the projector operator is representing. So, for example, the projector operator is representing the ith dimension here. So, it gives you the projection of the vector along the I. Right? It is the component, it gives you the component. It gives you the component of V along that direction in which PI is related to. We can say, if we say in three-dimensional I is equal to what? If I represents the x direction, right? Then this projector operator on the vector, that will give you the x component of the vector. Similarly, projector operator can work on a bra. So, if we have a bra V, the I acts on it, right? This will give you V, right? Into I, into I, right? And this is equal to. This is equal to, right? So we know that this is equal to what? That is equal to VI star, the complex conjugate of VI. You know, we have done this. Like VI is equal to IV star, or IV is equal to VI star, the complex conjugate of VI. So the same thing, right? When it acts on a bra, the projection operator works, can act on a kit, giving you this thing. It can also act on a bra, giving you a result like similar, right? Okay, what is now the product of the projector? Product of the projector operator. Suppose we have one is P I into P I, right? So we are going to apply this product to a pit width, right? When this acts on it, right? This gives, we said, PVI is equal to I into VR, right? So it is equal to I into VR, right? Again, what is PR equal to? We can, this is a scalar quantity, we can build it here. We are, it's just a scalar number, right? And PI is I, and here this right? And I equal to 1. So this is equal to VI into I. So this is now if we go back here, right? That is equal to the action of P on vector V. Here, we put here VII. This is equal to VII, and this was equal to PI acting on kit V. So here, what we get here, PI into V is equal to PI into V. That is equation number 5. So from equation 5, okay. So look at this one from equation 5. This implies that PI is equal to PI. Right? So the action of 2PI is equal to the action of single PI. In general, I will say P squared is equal to P. P squared is equal to P. It is like, this can be understood from the fact that if you have a Polaroid and light is falling on it, the Polaroid will only allow light that is parallel to the axis of the Polaroid. So that part, the component of electric field of light will go through, which is parallel to the easy axis of the Polaroid. If you put another Polaroid there, nothing will happen. You will get, if you will put another here with the same easy axis, nothing will happen. You will get the same thing. Light is passing, you have put a polaroid, so some light will be absorbed and sunlight will pass through. That light will pass through, which has its component, electric field component, parallel to the easy axis of the polaroid. Right? So if you put another polaroid, if I consider the polaroid as an operator, so it only selects a particular component of light and allows it and rejects the other light. So there is like picking a certain component, right? Projection operator. And if you put another polaroid, you apply the projection operator again on the same axis, nothing will happen. You will have the same thing. So the action of two projector vectors, two projector operators, sorry, not vectors, two projection operators, the action of two projectors is equal to the action of a single projector, the same thing. So this is important result. We will use it in our matrix algebra. Okay. Suppose we have like two different operators, right? They will be like this, J and J, right? That would be equal to what? You know, I and J, that will be equal to 0. So again, like polarized situation, right? They are orthogonal operators. One is along I, the other is along J. So light is falling on a polaroid, the easy axis. So it allowed a certain light that is parallel to the easy axis of the polaroid. And if you put another polaroid completely perpendicular to the previous one, then it will block all the light. Two polarides with one easy axis like this, and the next one easy axis like this, perpendicular to each other. So light is coming from here. It will absorb and only allow light parallel to this line. The vibration of electric field parallel to only this one. So if you put another polaroid perpendicular to it, it will completely block the light. So it is like 0 will be. So the same thing is here. Two projectors, when one is perpendicular to the other direction of one is like that, perpendicular to the other, that will be like 0. So we can write all the relationship in a simple PI, Pj is equal to delta Ij into Pj. We can remember this and this property and this property by a single equation. Pi Pj is equal to delta Ij and to Pj. J map you can put it equal to 1 by 2 or whatever. You can write it as I as well. Okay. So what is the matrix form of the project? matrix form of the project. Right? I kit and some n dimension can be represented by some column vector 0, 0, 0, 0, 1, 0, 0, 0. Where I, in this only, the ith component will be like you can represent it by 1. Right? Similarly, a bra I will be equal to what? 0, 0, 1, and 0 in n dimension. And your book represents the row matrix by putting a comma in it. Generally, rows do not have commas, but he puts it like this in the row vector. So I am putting it here as well. Okay, now you do it like this. I, and I will be equal to, right? 0, 0, 0, 1, and this only the ith dimension has a number 1, right? This is like n rows and 1 column. So can be represented by this pair, and this is 1 row and column. So this comes out an n by n matrix. Comes out to be an n by n matrix. So we can write this like here. An n by n matrix. 0, 0, right? And 0, 0, something, and 1 here, like 0, 0, 0, 0 everywhere. This is an operator. Remember, we represent operator by square matrices. So this is the square matrix with having one only in one place, and which belongs to the dimension that we are interested in, right? Generally, we can write this matrix in a short form, right? PI, right? KL, or row K and column F, and whatever we are interested in, the ith element, right? That can be written as K and to I and I and to F. K into I into F. And this can be written as delta Ki and delta I. So the projector operator with dimension I, we can find the element of this matrix by this equation, right? Delta Ki F. We will get a 1 if they are all the same. It's like, look, this thing K rho, it's like this, P I, right, and K rho and L column. This is the matrix element. This thing, right? Are we just put I in place of this, and we get this thing, and we get this relationship. This is how to find the matrix element of the projector operator in row K and column F. Matrices of the product of operators. Okay, suppose we have product of two operators. We have two operators, omega and lambda. We have two operators, omega and lambda. So the matrix element of the product, this will be the product after two operators. The matrix element I, J. I through J. Everything written is I, omega, lambda, thank you, J, right? With no problem, we can insert an identity operator in the middle. Because identity operator is equal to 1, it does not have any effect on anything. So we can write it like this. We can write it like this, right? I can write it. This I is equal to I, right? And omega and I K lambda and J lambda and omega are operators, and I replace the I operator by I is equal to K starts from 1 goes to N and K. Right? It starts from 1 here and goes to N. Right? If you look at this, this is the matrix element of the operator omega, and this is the matrix element of the operator lambda. So this can be written as is equal to, right, summation omega. This is omega I K, right? Where K starts from 1 goes to N. And this is the matrix element of lambda, and that will be lambda K and J. So this is how we get the matrix element of the product of two operators. It is the matrix element of the product of two operators is the same as this thing. We sum over the element K, we sum over it, and then it is like the product of the two separate matrices, right? And a sum over this. So we can get the matrix element belonging to column I, belonging to row I and column J, right? The matrix element of the product that is equal to, this is the matrix element of omega, and this is the matrix element of lambda. And but sum over k is equal to 1, 2, n. Whatever the space, the whole space is. Summing over the dimension of the whole space. So we will get the product of the matrix element of the product of two vectors from this equation. Suppose this is equation number 9 or whatever. Okay, what is the adjoint of an operator? The adjoint of an operator, right? If we have an operator omega, its adjoint will be represented by omega dagger. That will be represented by omega dagger. So we know that if we have an operator acting on a kit V, we can write this as this. Right? Similarly, if we have an operator acting on a bra, if this goes out, we write it like that. So, if we say this is an operator which turns kit V into some V prime, then omega dagger or the adjoint of this operator is an operator which turns a bra V. It acts on a bra. It turns it into some bra V prime, right? Matrix form of the adjoint, right? So we can write omega dagger Ij is equal to I and 2 omega dagger into J. That is the matrix element, right? And that is equal to this dagger acts on the bra can come inside and to J. Right? R we can write it as J here and omega and I here and making a star, right? We have done this, making a star, right? And this, when it comes out of the kit, it does not have any change. So that and I and star. So look at this. Omega I J dagger, right? The ith row, the column element of the dagger is equal to the action of omega, but rows turn into column. These are, look, rows turn into column and columns turn into rows, right? And then take the complex conjugate. The same thing. Make a transpose. If you want to get the element of the adjoint of an operator, adjoint of a matrix, right? Just change the places of I and J, and if it is a bra, change it to kit. If it is a kit, change it to a bra, right? And action of this, right? And take the complex conjugate of it. And what it gives you? It gives you the adjoint of that matrix. Right? So this is how we get the adjoint. Or we will say omega I J dagger. Omega I J dagger is equal to omega. This is dagger is equal to omega J I. Omega J I. This is J I. Omega J I and star. So if you want to get the matrix element of the adjoint of a vector, adjoint of an operator, sorry, the adjoint of an operator, you will just switch rows into columns. Look, this is I is now in the row, here it is in the column. J is in the column, here it is in the row. So interchange the rows into the rows and columns and make a complex conjugate of it, and you get the element of the matrix. Or you get the whole matrix. So we can say that the adjoint right transpose conjugate. Okay. Yeah. Right? What is the adjoint of a product of two operators? Right? We have omega, right? And lambda. What is the adjoint of it? What is the adjoint of the product of two operators or two matrices? Right? So we know that if we have some vector V and a product is acts on it, this will be equal to, right? This will be a very simple. I'm not putting I and J here, right? It will be equal to omega, sorry, will be equal to V and to omega lambda into star, right? And also lambda omega lambda and to V, this will be equal to lambda V and to omega star, and here this x again, so it will be equal to V, and that will be lambda star and omega star. So when you compare these two, we see that omega lambda star is equal to lambda star omega star. If we take the similarly for that was for a complex number, but for an operator it could be like extended in the same way. We take what omega lambda bigger will be equal to lambda bigger and omega bigger. So you should represent, you should remember this. You can write here instead of this, you can write the bigger 2. As we have done in the previous case. So we do not need to write star, we can just simply write bigger for this. Okay, so the adjoint of an equation. What will be the adjoint of an equation? Right? If we have some equation in a vector space, A1, V1 is equal to A2, V2 plus A3, V3, V3, V4, V5, right? Plus A4, M2, omega, and lambda, and V6, right? So what can we do it, right? If you want to remember the adjoint of an equation, we reverse the order, right? Reverse the order, right? And put what? And change, we will say, V, right? Into change this into it. and replace this by omega dagger, etc. And then A by a star. So the adjoint of this equation will be then the adjoint of this equation. We have to turn A1 to A1 star in each factor. V1 to V1 cross is equal to, now this thing, right? A2 to A2 star, V2 bra to V2 kit to V2 bra plus this thing. So remember, reverse the order here in each factor. Reverse the order in each factor too. So we will write it like this. V5, we will write first of all, we will write this thing. Plus, and this will be changed to kit to bra. So V5. Then there is a bra, so we will make it kit. V4 kit. There is another kit, we make it a bra. V3. There is A3, we make it A3 star. Right? Plus, here again, we have to change the order. Right? So it will be like V6. So we make it V6 bra. And now this thing, so we say change the order and change this to the dagger form, right? So we will put lambda dagger and omega dagger, lambda dagger, omega dagger, and then F4. And we will change F4 into star. So this is how we will get the adjoint of an equation in a vector space. Right? This is the equation. So what we do, we change the number to its complex conjugate. We change a kit into a bra. Right? So we did this here. We did this the same thing for here. Right? And you can do like this for here. It is a scale is a number, so it does not matter. It's a number. If you put it here to this side, it can be written as the same like this. V1 A star is equal to here V A1 star A2 star 2 or this. These are the same because this is just a complex number and it does not matter if you put it anywhere in the product. So it's the same thing as this. Here, so if you can write it this way or this way, the same. Okay, for the second term, you switch the order again. So I start from here. I start from the end. I start from here, but make it a bra. It's a cat, so I make it a bra. It's a bra, I make it a kit. It's a kit, I make it a bra. And then I write for A3 star. Similarly for this, I start from V6, but make it a bra. This, I reverse the order. Right? So I write lambda first, but put change this to the dagger form. So lambda dagger, then omega dagger, and then F4 star. So in this way you can write the equation in a linear vector space. if you want to write the adjoint of it. Permission operator. Permission operator, right? An operator will be Hermitian if it is equal to its adjoint. So if we have omega as an operator, so it will be Hermitian if its dagger means adjoint is equal to. So an operator will be Hermitian if its adjoint is equal to itself. We call it Hermitian operator. Anti-Hermitian. Right? If you take the adjoint of an operator, it comes out to be a negative of itself. Then the operator is said to be anti. If you take the adjoint of an operator, it comes out to be negative of itself. Then this operator, this will be called anti-Hermitian operator, right? Just like a complex number. If we have a complex number, we take its conjugate, we get a negative of it. This is something like a real number, this is something like a complex number. You take a real number, you take a complex conjugate of a real number, you get the same thing. And if a complex number or imaginary number, right, you take complex conjugate of it and you get negative, right? So it's the same thing. We can splitting of an operator into Hermitian and anti-Hermitian part. We can split into anti-Hermitian and Hermitian part. Like, we can split a number into its real and imaginary part. We can split a number into its real and imaginary parts. Similarly, we can split an operator into Hermitian and anti-Hermitian parts. Right? It could be like this. Omega would be equal to omega plus omega dagger divided by 2, right? Plus omega minus omega dagger divided by 2. This part is Hermitian. And this part is anti-Hermitian. It's like a complex number. We can divide a complex number into purely real and imaginary parts. If you go back to your complex numbers knowledge, complex variables in your mathematical methods of this course or your mathematical methods course in masters or in MPhil. So you will see that you can split a complex number into a purely real part and a purely imaginary part. unitary operator. Unitary operator. You know, if we did the rotation operator quite in detail and was in 3 dimension, rotating it by pi by 2. We did it a lot, right? We can do it rotating a frame by any angle, right, in 3 dimension. This unitary operator is an analogy, having analogy with the rotation operators in 3 dimensions. So this is an analog of the rotation operators, right? Uh, for n-dimensional space. Right? So an operator is said to be unitary. Unitary operator, the U is unitary, an operator. An operator is unitary. An operator is unitary. An operator U is unitary if U bigger and U is equal to R. If you multiply it by its adjoint, and what you get is the identity matrix, right? Then U is a unitary operation. Similarly, U and U star is equal to I. So an operator which has this property that you multiply it with its adjoint, you get the identity matrix. Then this operator is called unitary operator. Similarly, and the order does not matter. The order does not matter. It could be like this first and this second, like this first and this second. But you get the identity matrix or the identity operator. Then it is like this operator is unitary. So these are all uh, parts of the grammar that we have to learn the language. You know, the language that we are learning, the language of solving quantum mechanical problem. This language we have to learn all its grammars, rules, and regulations, and whatever. So these are all the rules and regulations that we are trying to learn the language, this new language. We have to keep all these things in mind because we will use them in our future work. Uh, Let us finish this work here, and I will see. Homework. Exercise number 1.612 star and 1.6.3 star. This is your homework. So next time when we meet, I will just send you the invitation, and till then, I'll see you off. Any question now? Any question at the moment? And your attendance, if somebody has not put his or her attendance, somebody who was not present at the start of the lecture and has come late, we can put your attendance here.
Sir Izadul Haq.
Izazul Haq?
Yes, sir.
Izazul Haq. Okay, so how many people have left? Still we are only 10 people. Izazul Haq. Okay, then Muhammad Asim Safi. Remember, we will have to take the attendance in the start of the class then in the future.
Sir Muhammad Zahir Islam.
Huh?
Muhammad Zahir Islam.
Muhammad Wahid Islam. Remember, I will take the attendance in the start again next in future. Muhammad Asim. What is your name?
Muhammad Zahir Islam.
Muhammad Zahir Islam.
Yes,
Okay,
sir.
good. Okay, see you then.
Okay, sir. Thank you.
Now you can leave the meeting by clicking on the red phone symbol.